Swayam Prabha. Digital India. Educated India.
Welcome to the next module of this ionic polymerization. Now, if you recall that previously we discussed about the cationic polymerization of carbon-carbon double bond. In this head, we discussed about the various initiation protocol for this cationic polymerization. We discussed about the photo initiation effect. We discussed about the radiation induced initiation steps, etc. Now, in this particular chapter, we will discuss about the propagation, chain transfer and termination and the kinetics of cationic polymerization. So, because this particular lecture deliberated more towards the basic mechanism of this cationic polymerization. So, let us have a look about this propagation step. Now, in the propagation step, the initiator ion pair usually consisting of carbocations and its negative counter ions. So, these two things counter ions they produced usually in the initiation step, with the example of, say, if you recall in the previous lecture we discussed about the boron tetrafluoride. In continuation process, if you recall that we discussed a lot of various techniques for this initiation step. Now, this further proceed to propagate by successive addition of monomer molecules. So, let us have a look about this particular aspect. CH2C this which we developed during the course of our initiation process, and CH2 double bond CH2, this may gives you HCH2 C CH3 CH2 C CH3 twice BF3OH. So, this facilitates the further propagation of these things, or sometimes in a very short form, if we would like to refer, that it may be represented as FIZ plus M. Now, this is the more appropriate form to represent in the reaction engineering concepts. So, when we try to develop the reaction mechanism, then it facilitates the things. If we talk about this particular addition process, usually it is by the insertion of monomer between the carbocation and its negative counter ion, as discussed in the previous reaction. Now, sometimes isomerization, polymerization need to be addressed. Now, the propagation reaction, this can be complicated in some cases by the occurrence of intramolecular rearrangement, because it is a suo moto habit of all these polymer chains for this intramolecular rearrangement. So, the polymerization proceeding with rearrangements, they are referred to as the isomerization and polymerization, and when we need to address this issue, one must be very selective in this approach. The extensive rearrangement during the propagation usually occurs for a variety of alkanes, usually referred as alpha olefins. The best examples are propene, 1-butene, and higher alkenes. Sometimes they yield to oligomers with highly irregular structures due to the various combinations of hydride or methide shifts. So, the propagating secondary carbocations, they are insufficiently stable to propagate without extensive rearrangements. Simultaneously, only oligomers they are formed since none of the rearrangement pathways are favorable for rapid propagation. So, the extent of rearrangement during cationic propagation usually will depend on different factors. One factor is the relative stabilities of propagating and rearranged carbocations and the relative rates of propagation and rearrangements. Now, these both factors, they favor the propagation without rearrangement of for monomers like styrene, iodine, indene, and sometimes chemorone, vinyl ethers, isobutylene, etc. Now, this is one of the structures of styrene, indene, isobutylene. You can see over here. Now, these are the structures which are equally important when we try to develop the rearrangement patterns under the edges of isomerization of those polymeric species or the under polymerization process. Now, not only these monomers propagate via reasonably stable carbocations such as tertiary, benzyl, oxycarbocations. The carbocations have no routes available for rearrangement to more stable carbocations. So, it is a very, you can say, the tedious type of a situation. Now, isomerization, polymerization yield high molecular weight products. So, when reaction proceeds further through a relatively simple rearrangements route involving stable carbocations. Now, when we talk about the chain transfer and termination, various reactions sometimes led to the termination of chain growth in cationic polymerization reaction. Now, see these two things, the chain transfer and termination, both are equally important compared to the propagation. The reason is that whenever you require the polymer to have a desired property, then you need to truncate the polymerization at appropriate time and appropriate juncture. So, that is why this chain transfer, sometimes you may transfer the charge, sometimes you may transfer the radicals, and by any means you need to terminate the things. So, that is why this particular concept is extremely important to address. Now, many of the reactions, those who terminate the growth of a propagating chain, sometimes they do not, sometimes they do. So, the termination kinetics chain or termination kinetics need to be addressed properly. Now, terminate the kinetic chain, sometimes there may be formation of a new propagating species is generated in the process, and sometimes it is quite advantageous, sometimes it is disadvantageous. Now, the disadvantageous may sometimes it may promote to the formation of other polymeric chains. Those polymeric chains sometimes may not be desired one. So, these propagating species sometimes referred as the beta proton transfer. Now, the transfer of a beta proton from a propagating carbocation is the most important chain breaking reaction, and that decides the property of the polymer. Now, it occurs readily because most of or much of the positive charge of the cationic propagating center resides not on the carbon, but on the beta hydrogen because of the hyperconjugation. We have already discussed this hyperconjugation concept. Now, monomer counter ion or any other basic species in the reaction mixture can abstract the beta proton. The chain transfer to monomer sometimes involved the transfer of a beta proton to monomer with the formation of terminal unsaturation in the polymer. Now, let us have a look about some mechanism of this chain transfer and termination. Now, let us see this particular chemical reaction. CH3 hold twice and CH2. See, now this is the positively charged CH3, and I am referring the previous examples in this reaction. Now this is CH2 double bond C CH3 twice. This may gives this CH3 C plus BF3OH negatively charged plus H. It is bonded with the CH2C CH3 CH2 plus H CH2C CH3 whole twice CH3 whole twice. Now sometimes for the ease of explaining the mechanism, we may refer to this like HMN plus IZ plus reacts with monomer. This is the termination or transfer rate constant. This may be Mn plus 1 plus Hm plus Iz minus. So this is the basic mechanism of this chain transfer and termination. Now there are two different type of beta protons and two different type of unsaturated end groups. Now these are possible for if you take the example of isobutylene as well as some other monomers such as indene or alpha methylstyrene, etc. Now the relative amount of two end groups depend on the counter ion, identity of the propagating center and other reaction conditions, because sometimes during the designing of the reactor or sometimes during the designing of a reaction mechanism, this particular information is quite important. So because people may interested to have the knowledge about the relative amount of these two end groups. So that depends on the identity of propagating center and other reaction conditions apart from the counter ion. So only one type of unsaturated end group, that is referred as internal group, is possible for other monomers such as styrene, ethyl vinyl ether, etc. Now it should be pointed out at this juncture that the kinetic chain is not terminated by this reaction, since the new propagating species is already generated and it is equally active in the reaction mass. So therefore it is not being terminated. You can't say that there is being terminated. Now chain transfer to monomer is on much more favorable term with the propagation in many cationic polymerization compared to the radical polymerization. Now since it is kinetically indistinguishable from the propagation, the relative rate of transfer and propagation usually given by the ratio of usually KTR m upon Kp, this KTR m upon Kp, which is the chain transfer constant for monomer Cm. The value of Cm usually, this is referred as equal to the Cm, the value of Cm determines the molecular weight of the polymer if other chain breaking processes are not significant. So again your molecular weight distribution plays a vital role. Now the larger the value of Cm, the lower will be the molecular weight. It is quite obvious to this particular mathematical equation. Now chain transfer to monomer is the principal reaction that limits the polymer molecular weight for most monomer, especially at reaction temperature higher than say about 20 degrees Celsius. Now since the chain transfer to monomer generally has a higher activation energy than propagation, it is usually suppressed by working at a low reaction temperature. Now chain transfer to monomer reaction involving the hydride ion transfer from monomer to the propagating center For the case of boron trifluoride is referred as HCH2C CH3 CH2C BF3OH minus plus CH2 double bond C CH3 whole twice, then CH2C CH3 CH2 BF3OH plus H CH2C CH3 then CH2CH CH3 whole twice. So this is the basic reaction. Now chain transfer to counter ion involves chain transfer to counter ion. This involves the transfer of beta proton to the counter ion. Now the initiator and co-initiator is regenerated by its expulsion from the propagating species, and as in the chain transfer to monomer, the polymer molecule has a terminal double bond. So it can be represented like this: CH3 whole and now CH2C plus, you see over here that